Hello, everyone. So this is my second video. In the previous video, I just showed you how to, or it was a walkthrough of the system module design that I created. In this video, I just want to show you like the first steps and trying your custom board and just writing a simple Blink application and to test the functionality, the connection, and at least you have the microcontroller up and running. So the first thing that we are going to do is going to be open your Cube IDE or CubeMX. I like to use Cube IDE, and I'm gonna create a new project. Sometimes it takes a little bit. All right, so here we have the selector. I'm gonna select, oh, still thinking. All right, so I already have in my favorites the L443. Yeah, it's gonna be this one. So we're gonna name our applications just Blinky application of the system on module. SOM, let's call it 433. You can call it however you want. We'll click yes. So you can follow along with your own Nucleo board or custom board if you have one. In the video, I'm gonna try to create a Blink application, but using the timer interrupts, because even though the creating a delay using the HAL or the high abstraction layer hardware abstraction layer delay function, which holds the microcontroller for as long as the wait time that you defined. That's good for testing the functionality of the board. Is not how you would do it in a in a real application. So I'm gonna take the approach of doing this with the interrupts, and and it's a little better way to do it. So the first thing, I'm gonna come here to system. I'm gonna enable the debugger serial wire. You could use serial, well, I could do serial wire or a trace asynchronous. This just includes, but this is how I have configured uh, the SOM and the 6-tick timer. Now here I'm gonna enable my crystal oscillator, the external crystal oscillator. And if you are running maybe a Nucleo board without the external crystal oscillator, you might want to use either the internal RC oscillator or use the bypass clock source to use the MCO coming from the ST-Link. So next step, we go here. In my case, I have a 24 megahertz crystal oscillator, and I want to run this at 80 megahertz maximum frequency, so everything is running at 80 megahertz. So I come here, my LED, the onboard LED of the system on module. If we go to KiCad, I have that on the timer 2 channel 1, which is connected to PA15. So PA15 is here. I'm gonna enable it as an output, and I'm gonna give it a label, more descriptive label. It's recommended to do that. And once it is defined, now let's add a timer. So I'm going to use timer 16. This timer is going to be dedicated to flash or blink the LED. So it doesn't need to be one of the more advanced um, timers unless you want to use a PWM, the PWM channel or something like that. So I'm just going to activate it. So the prescaler. So the clock is running. If we go here, the peripheral clock, the timer clocks on APV1 and APV2 are running at 80 megahertz both. If they were different, you just have to go to the datasheet to verify where your timer is connected to which bus is connected. So in my case, both are, well, all of them are running at 80 megahertz, so it's safely to assume that my internal clock for timer 16 is running at 80 megahertz. So I'm going to bring this down to 1 megahertz, just easier for the calculations. So my prescaler is gonna divide the clock frequency by 80. We have to subtract 1 from here. And now that is 1 megahertz. If I do my period or auto reload to 1000, that's gonna create a cycle of 1 millisecond. So I'm gonna enable the auto reload. So every time that it overflows, it starts back again. And I'm gonna enable the interrupts for that timer. So if I go here to my NVIC and I have the interrupt enabled, I'm just gonna change the priority. I'm gonna set it to 10, kind of like in the middle. You can leave it at 0 if you want. If you just want to test, or even 15, that's fine. So that's everything on this side. I'm gonna just save everything and generate a code. Yes. So it's gonna take a minute to generate a code. That's just it. So now here we have. So usually what we would do if we are testing, now just create a simple blink application. It's going to be just create a or toggle the LED so we can use a HAL GPIO toggle function, and we call here the toggle function and create a small delay, the built-in delay, and we say, oh, let's do it 1 second, 1000 milliseconds, and we can save and build a project, and everything is good. We flash it to the board and it should work. But that's not what I want to do. So we want to use the interrupt to do this. So before, let's delete this. So in order to use our interrupt to do this, so the first thing is we need to start the timer, right? So if we start the timer, we can't call the whole time start. Oh, actually it is whole time base start with interrupt, and is our timer 16. So that's going to start the timer. So now every time that it or every millisecond is going to generate that interrupt. So if now we need to also the Cube IDE generate all the drivers for our peripherals. So if we go to the timer, we say yes, I don't want warnings. Okay. So we are going to locate the whole timer callback function. That's here. So this function is called every time that the timer overflows. So, and is defined as weak, so we can override this function in our code. So we go, usually I go to the bottom here in this section, and remember to write your code inside these kind of guards that Cube IDE generates. So when you regenerate the code, it doesn't get deleted. So here, first, I want to check if the actual interrupt that we are receiving is coming from the timer 16. And to that, I'm gonna check that the instance of the interrupt is equal to team or timer 16. If that's the case, then we process our interrupt. So go here, okay. So now when we receive the interrupt, we are going to start our timer. All right, so you know what? Let's change this approach. We're still using the interrupt, but we are gonna use it in a different way. So let's say that we want to reuse this code because we are building on different applications, and in all of them we want to flash the LED. So it would be nice to have some code that we can reuse and easily integrate on every project and don't have to do this like from scratch every time. So in order to do that, we still are going to keep this because it's going to be necessary. And because if you have another timers for different purposes, you want to differentiate which one is generating the interrupt for your LEDs or whatever other function you are using. So we are going to add our custom like drivers. So we are gonna add here another source folder, and we are gonna call it like just custom drivers. All right, so inside there we are going to create a header file, which is going to be our led.h, and a source file, which is going to be led.c. So here we are going to include our led.h. That's good. And in led.h, we are going to include our main.h, and we are including main.h because here main.h we have the all the definitions for our microcontroller. So we want to do that for this. All right, so now we have defined our led.h. We want just verify that this folder is going to be so you don't want this to be checked because it's going to be excluded from compilation. And also we want to add our the files, the led.h to the path. So include paths on the assembler GCC compiler. And it is here. We're gonna add it from here. Custom drivers. We click OK, OK, apply, and close. So now it is included. I think we can compile, see if there's any error. So it is good. All right, so now we want to or the way that we want to do is we are going to create like a init LED init function that we can call to initiate the LED, and in that function we are going to include or start the timer, which in turn is going to generate an interrupt, and that interrupt will help us to flash the LED. And the way that I want to flash the LED is gonna be in the off state for a period, and in the on state for another period. But I want the on state to be very short compared to the off state, so that will give us the effect not just to blink the LED at the same rate, not at the same rate and the same interval for the off and on state, how we normally do it, and I just like create the effect of a quick flash of the LED every second. So we are going to have it in the off state for 0.9 seconds and 0.1 seconds in the on state. So, and also before that, I'm going to change the frequency of the clock, the timer clock, because right now we have it for every 1 millisecond, and I want to have it like this at a like even slower than that, because this is a 16 bits timer. So if we generate an interruption at the maximum value, which is 65,000 or approximately 65,000, that would give us just 65 milliseconds delayed, and we don't want that. We want to have like a larger delay. So if we bring our calculator here, right now we have our clock at 80 megahertz, and we want the prescaler to be, sorry, we're gonna divide by 8,000. That brings down our timer clock to 10,000 hertz. So if we, which is 0.1 milliseconds per tick. So we're gonna take that, and if we want 0.9 second delay, the longest one, we divide this power by the period of our clock. Is the value is going to be 9,000. So initially you want to divide by 8,000, right? And the first time we have here, we're gonna find it at 9,000. This value is not critical because we are gonna modify this in the code. So let's find, we generate the code again. All right, so the first thing that we want to do is create our function to initialize the LED. So let's call it like LED init, and this function is going to receive the timer, the handler of the timer that we are going to use for to do this, and all, and just that. And we'll create another function to update the LED on every interrupt that is going to either turn the LED on or off. So if we go now to our drivers code, or we can get that from the main. All right, so we're going to create a pointer to this of this type to actually point to the timer instructor. All right, so we are going to receive a pointer. Oops, let's do it like that. It's a pointer to the timer, right? And now just save it, and now we go here to define our function. What's happening? All right, so in this function, so here we want to receive the timer structure and kind of like do these more reusable, so we don't have to like hard code in every function or every line of code every time that we refer to the timer structure. So I'm going to create a pointer here. It's gonna be our LED timer. We can initialize it to null. That's fine. And here, when we receive that, we're gonna say that LED timer is equal to timer structure. So that way now we have in all this file a reference to that timer structure. So now we can call our function to start the timer. That's it. So now we start the timer. The timer is going to start running and it's going to generate an interrupt. In this case, the first time. We define it at 0.9 seconds or 900 milliseconds. So, okay, so now we need to define the function to update the LEDs. And this function is going to be called every time that we receive the interrupt or the interrupt occurs. So here we are going to create or receive the time for that the LED is going to be off and the time that the LED is going to be on. So we're going to do a 16 bits variables because our timer is 16 bits. So there's no point to create a bigger variable. And let's call this LED LED period high, LED period low. All right, so now we want to update the LED according to the state of the LED, right? So so we want to read the current state of the LED. For that, we are going to use GPL read function. right, so if the current state is on, sorry. All right, so if the something wrong here. It's not hot. All right. All right, so now it's correct. Okay, so if the LED is on, first thing we want to do is turn it off because it corresponds to the next state, and we're gonna use the same GPIO. Now the write function. So write, oops, LED port. LED pin, and now it's going to be GPIO pin reset. So now we want to, let's say that the timer, if the LED is on, it means that the period of the timer was the smaller one. And now we want to change the timer period to the off state, right? So to do that, we can use some macros defined by in the HAL hardware abstraction layer, or the HAL library, and those are, we can change some parameters of the timers on the fly, so we don't need to initialize the structure, initialize the timer again. So we are going to set the counter again, and we gonna pass the handle of the timer, and we gonna pass the count that we want to write, which is 0. Now we are going to set the reload or auto reload, auto reload LED timer, and the auto reload value. So as I said, if the GPIO pin is set, so it's 1, now we want it in the off state, and the larger time is going to be this low value, or the period where the LED is going to be in low state or off. So we're going to take this. All right. And now we can start the timer. Use this to start the timer. So if we start the timer again, so we don't need actually the timer to have this auto reload enabled, because every time that we receive the interrupt, we'll enable again the timer. So we don't need the auto reload because we are initializing the timer here again. So if the timer is 1, we reset. Now we wait for the interrupt to occur. There's going to be 0.9 in case if the timer was the LED was in a state in on state. So now if it is not in on state, which is off, so we are going to do the opposite. We're gonna turn on the LED and do the same here. And now this is gonna be high. And we initiate again this the timer interrupt. So the interrupt is going to occur and call this again. So now that we have our driver written here, so we go back to the main.c file, and here we have to do a couple of things. And the first one, after all the initialization of our peripherals, so here instead of initiating the timer here, so we are going to call our LED init function, and in order to do that we have to include here our led.h. So now here when we call this function, is gonna init this timer, and we need to pass the handle structure of the timer. So that's h, oops, htm16, if I'm not mistaken. Yeah, htm16. So now down here, so when the interrupt occurs and verify that it's coming from our timer 16, so here we're going to call the LED update function, and this in here we are going to pass these two values. So the period where the timer is going to be on, and the period where the timer is going to, or the LED, I'm sorry, is going to be off. And so we don't want, or best way to do it, we could do here, let's say it's high and low, so on and off. So in the on state, I just want to be short time, and here in the longer time. So in total is going to be 1 second, but it's 0.9 seconds off and 0.1 seconds on. We can do this, and it probably is going to work. Actually, we can compile and see if we have any error. We have led.h, it cannot find it. Let's see, it's not finding that. All right, let me figure it out, and I'll be back. All right, so I had a few mistakes. I still don't know why it wasn't taking this folder as a like include some header files, but I ended up was deleting folder, created again, and also give it the full path of the led.h file. And I also had I had forgotten to define this in the .h file, and so I added that function here and just added these guards in case of the C++ defined. This is C code. So now it's compiling without errors. So as I was saying, I could just hard code these values here, but this is not what we would normally do in a proper program. So I'm going to define these values here on top. So we in case we are referencing those values somewhere else, we have only one place where we can modify. So I'm gonna create here LED off, and in off state it's gonna be 9,000, and in the on state it's gonna be 1,000. And now we can pass those values here. My LED on and LED off. All right, so just verify this is the order is on off. So on is the period high and off is low. So here we are setting, so turning on with height period and initiate it. So that should be it. So we can compile again. That's good. And now we can debug. So in our debugger, everything looks correct. Yep. So we can click OK. So it's going to start the debugger, and now I'm going to change the camera to show you the actual LED flashing or blinking on the actual board. Right, so here we have our debugger, and I'm gonna restart the debugger. We have it here. If we press play, now the LED is gonna start flashing. So there you go, the LED flashing. As you can see, that's the onboard LED. This one here, and it's off for a longer time and is on for just a short time, just flashing, indicating the program is working. So here we have the other LEDs. We can also try to work with this in future videos, maybe using the PWM just to have some more or different effects on those LEDs. So there you go, guys. That's the LED or the board working. So now in this way, you can actually add these two files to any project, and we also can define here another functions like the init, the timer, and the LED. And if you no longer want to flash the LED for any reason and activate it again later, but in this way you can add these two files to any project, and in the main file it is like a minimal the code that you need to write in order to flash the LED, and you don't have to do this over and over again. Just do it once and have your own custom driver for the LEDs. You need to initialize passing the timer handle, and inside the interrupt service routine, just update the LEDs, and that's it. So I hope, guys, you learned something new today, and this is helpful for you. And I know the video is a lot longer than I anticipated to, but but I hope it was good and you learned something different, or at least with a different approach of what we normally see, that just uh, turn the LED on, call the delay function, and uh, and off again, just holding the CPU of doing any other task other than just waiting for the timer to time out and turn on and off the LED. So here, as you can see, we don't have anything in the main loop, and the CPU could do any other tasks or more important task actually than just flashing the LED. So thank you guys, and see you on the next video.